This problem you're going to find in almost any introductory physics class. So to me, the purpose of this problem is to illustrate the use of the equation constraint. It's not the simplest problem for that purpose, but it's not the most difficult either. So we have two boxes connected by a massless string, and the string is hung over a massless disk. So what is the meaning of massless string and massless disk? Well, first of all, the massless string simply means that the tension is exactly the same throughout the string. The massless disk means it does not play any role in the dynamics of boxes A and B, so we can ignore that in terms of the free body diagram. We're going to assume we know the masses of the two objects, and we're going to assume we know the coefficient of kinetic friction between the table and block A. So we've done the sketch already. The next step is the free body diagram. So I'm going to draw box A. It's going to have a force of tension, and I will put a subscript A on for now. We're going to have a normal force. There's only one normal force in the system, so I don't need a subscript to differentiate them from each other. We have a force of gravity acting on A, and then we have a force of kinetic friction acting on A. So that's the free body diagram for A. For box B, we're going to have a tension force on B, and then a force of gravity acting on B. Okay. That's it for the free body diagrams. The next step is a reference frame. I'm going to make a quick little sketch down here. So here's box B. Here's box A. I'm going to extend the tape out a little bit down. I'm going to put a reference frame, traditional X and Y, a little bit to the side of box A. And the purpose for that will come clear in a little bit. And we're going to put the origin of the optimus right there. Alright, now we're ready to decompose the vectors. And if you're comfortable with it, confident, you can start skipping all the steps now as you want to. I'm going to just not skip steps. So first, we're going to look at the X direction. Let's get some ink out of this one here. Alright, so I'm going to look for the components acting on box A. So in the X direction, let's just look at all the forces. So we have a tension force on A. Its X component is simply the force of tension. So now I'm going to drop the subscript, knowing the fact that since it's a massless string, it's just tension. We don't have to differentiate between A and B. I did put them here simply because you can see they're different directions. So I want to make sure that we don't say these forces are equal because they're vectors. Same magnitude, but not same direction, right? All right, we're not being a component, so it's okay. We have the normal force. I don't have a subscript on that, so let's get rid of that. X component, it does not have X component, so that is 0. We have a force of gravity acting on A, does not have an X component either, also 0. We have a force of friction, it's kinetic, its X component is in the negative, so it's a negative contribution. And now we're going to use the tool or the equation that relates it to the normal force. Okay. And we should be specific that it's the normal force in the y direction because it's going to be a component that's perpendicular to our X. Alright, so no more forces along X for that box. Box B, we don't have anything in X, so the force of tension Bx is equal to 0. Force of gravity on B in X is also equal to 0. Now we can do I have room for Y here. Let's try and see if we can squeeze it in. Here's the Y direction. For A, we have a, let's skip a couple of steps here now. The tension force does not have any components, so that will be 0. Okay. So we have a normal force in the Y direction. That's a positive, and it's simply the magnitude after that. So the magnitude, normal force, positive to add it into a component. And then we have the force of gravity in the y direction is a negative component, and then we can substitute in our knowledge for the force of gravity, mass times acceleration of gravity. Force of friction doesn't have a y component either, so we can leave it at that. Box B, we have a tension force in the y direction that is in a positive, and it's just the force of tension. And then we have force of gravity acting on B in the y direction. It's a negative component, so it's negative mass B times the acceleration of gravity. Alright, let's see if we can have that in there. That's good. Alrighty, so now we're ready to insert all this into Newton's second law. We have two objects, so we're going to have two Newton laws, one for each object. So we're going to do, let's do x first. I guess you guys can see x first, okay. It's not a meaning, I just wrote x above here. So let's do A first, box A first. So the sum of forces in x, we're going to have plus the force of tension, and we're going to have minus mu, and the normal force in the y direction, we already know that's going to be normal force down here. So that's just the normal force is equal to mass A times acceleration A in the x direction. Okay. Now we do box B. We're going to get 0 is equal to mass times the mass of block B times the acceleration of block B in the x direction. This is a trivial solution, so I'm going to just strike out that equation. It has no use to us. Now in the y direction, for box A, down here, we have a plus the normal force minus mass A times the acceleration of gravity is equal to mass A times the acceleration of A in the y direction. And then for box B, we have plus the tension force minus mass B, the acceleration G is equal to mass B, the acceleration of box B in the y direction. Okay. So now we can count out how many unknowns we have. We're solving for the acceleration. The tension force is not known, normal force is not known, the three accelerations are not known. So we have five unknowns and three equations. This is not in our favor. So that means we need to go into the next step, and that's the equation constraint. So we have one constraint. So for example, we know that the y position of box A does not change. In fact, according to our reference frame, the y position will be 0. That implies that there's no change in the y position since the box is constrained to move on a horizontal surface. And again, that implies that the acceleration of box A in the y direction must be equal to 0. So that is 0 right here. So let's rewrite that equation as the normal force minus mass of acceleration, mass of A times the acceleration of gravity is equal to 0. Okay. So got that equation. We got that inside the screen. That's good. All right. Now we still have one missing equation, and that's the last equation constraint. And for that purpose, I'm going to redraw this in a little bit more careful manner. And I'm going to put the disk right here. Box B, box A. Okay. And then here is our reference frame. Here's Optimus standing right here. So we're going to say this part here, I'm going to actually go all the way over to where the string is. I'm going to call that the x position of box A. I'm going to say the table length. I'm going to call that for large L. And then we're going to say that the position of the box is going to be negative YA. So this is B. Okay. And it's going to be negative simply because Our origin is sitting right over here, so we have y being positive up, and we got x positive to the right, so this will be a negative component of this position of box B. Okay, I'm going to call the length of the rope for L. We know that the length of the rope is constant. So we can look at how much rope do we have right here. Well, that's going to be L minus XA. Okay, that's how much horizontal rope we have. How much vertical rope do we have? Well, that's going to be negative YB. So that's how much rope we have right here. So we add these two together, we're going to get the total length of the rope. Right. Now we know the length of the rope is constant. So if we look at the differences here, we can say the difference in L minus the difference in XA minus the difference in YB is equal to the difference in the length of the rope. We already know that I keep looking at my screen because I'm going to make sure everything fits into the video. We know the length of the table doesn't change, so this is 0. We know the rope doesn't change, so that's also 0. So what this implies is that the change in A position must be equal to the negative change in the Y position. And the implication of that is that, yes, we can still have that, is that the acceleration of box A in the x direction must be equal to the negative of the acceleration of box B in the y direction. So let's call it just for A. Okay. This is an equation of constraint that's a little more complicated what we've seen so far, but it's really how we solve a system that is connected or constrained to move in a certain way. So that's something we need to have practice with. All right, now let's use that to our advantage now. So here we have force of tension minus the coefficient of kinetic friction. I forgot it. This coefficient of kinetic friction. Let's put that in there. That's the normal force. Okay, equals mass A times the acceleration A in the x direction, but that's just what we call A for now. Okay, we have this equation right here that tells us this is the tension force minus mass B times the acceleration of gravity is equal to mass B times negative A, which is going to come from here. Okay, so this gives us, let's see what do we have now. Tension is not known, normal force is not known, A is not known, but we have 1, 2, 3 equations, 3 unknowns. If we were to, see again, have room here. So, for example, this equation here tells us that the normal force is equal to mass A times the acceleration of gravity. We could probably set it right away because these two forces must be balanced since there's no acceleration of box A in the vertical direction. Okay, now we can plug that into this one up here. So this is tension force minus coefficient of friction, but now we can write this as mass A times the acceleration A is equal to mass A times A. We have this one here, which tells us we have tension force minus mass B, acceleration of gravity is equal to negative mass B times A. Okay, so what I'm going to do is now we're going to actually take these two equations we have right here. I'm going to put a box around these two here. I'm going to subtract the second equation from the first. So I get force, the tension force minus the tension force. That's up to 0. Subtract. This one is a negative. That gave us a plus mass B times the acceleration of gravity. We subtract that from the first one. So we have this term here still. And then we subtract the bottom from the top. So as a minus up becomes mass A plus mass B times G. Sorry, not G. Times A. You guys see that already? No, there's no A. So let me erase this one here and write that down here. So that's equal to, the second term, we're going to shift in a little bit, it's going to be mass A plus mass B, because we're subtracting them, right? We're subtracting the bottom equation from the top equation. So it's going to be mass A minus minus, and then the acceleration. All right, so now we can solve for the acceleration, dividing by the combined mass of both sides. So it's mass B minus the coefficient of friction times mass A, parentheses, acceleration of gravity, divided by mass B plus mass A. So that's the answer for the acceleration. A lot more complicated process than some of the other problems we've seen, but it is one that really highlight the use of the equation and constraint. And I think that is the sole purpose of this problem.